AP Chemistry. So this is video number 3, part 3 of the day 81 assignment, and we're going to wrap it up with this video. So we're on question 14.63. And the question reads, what is the molecularity of each of the following elementary reactions? Write the rate law for each. Okay, so molecularity is simply how many different molecules are involved, different types of molecules are involved in a reaction. Because if it's only one type of molecule, so let's look at A. There's only one type of molecule, Cl2. So it's very easy for two Cl2 molecules to find each other and to hit each other. So that will be a very common type of reaction. That reaction should take place faster. If you have two different types of molecules, if you look at B, then they have to find each other. If two H2O molecules hit each other, that won't cause the reaction. Or if two OCl molecules or ions there hit each other, that won't cause the reaction. So it has to be an OCl and an H2O in some mechanism. So again, we saw that not everything happens necessarily in the first step or in one step. So it may be a couple of mechanisms involved. But the bottom line is the more different types of molecules you have, the more difficult it is for the reaction to take place, and therefore the slower the reaction takes place. So to answer the first question is, what is the molecularity of each? For A, it's unimolecular. There's only one molecule or one type of molecule involved. For B, it's bimolecular. There's two types of molecules involved. And for C, it's also bimolecular. If you have three different types of molecules involved, it's called termolecular, and those are very, very rare because that means all three of those molecules in some fashion would have to find each other and hit each other. And every time you add in a different type of molecule, a different compound, you reduce the odds that that's going to happen. So termolecular reactions are very rare. So anyway, the answer to the first part is unimolecular, bimolecular, and bimolecular for those three reactions. Now it asks to write the rate law for each. So let's go ahead and do that. All right, so here are the three reactions. The question does state that they are elementary reactions, and what that means is that you can use the coefficients of the reactants as exponents in the rate law. So it asks to write the rate law, so we'll go ahead, this one, we'll do it. And of course that's raised to the first power, although we don't write a 1 necessarily. You can do that. Again, coefficients for the reactants are 1, so the exponents there are 1. Okay, and there is the complete solution for this problem. Problem 1468. The decomposition of hydrogen peroxide is catalyzed by the iodide ion. The catalyzed reaction is thought to proceed by a two-step mechanism. The two steps are given there. So A, write the rate law for each elementary reaction. Write the chemical equation for the overall process. That's B. C, identify the intermediate, if any, in the mechanism. D, assuming that the first step of the mechanism is the rate determining step, predict the rate law for the overall process. Okay, so what we want to do first is go ahead and write down those two equations along with the words slow and fast off to the right. Okay, so there we have the two reactions right there, step 1 and step 2. You can't figure out these elementary reactions by looking at an overall reaction. It's something that has to be given to you. They're not obvious. They're not something you can figure out. But let's look at what's happening here. We start off with H2O2, and I- is going to be a catalyst, as you'll see. So what happens is this does something, and we don't know exactly what, but this does something to break this up. And what you end up with is H2O and IO. Then what happens is the IO that you produced in step 1 collides with more H2O2. So H2O2 collides with two different things in this whole process, an I- and an IO-. And in that second step, it produces H2O plus O2, and then the I- comes back out. So what you have is the I joining an oxygen here. It stays, when those two come down to the second step, they collide with another H2O2, and it actually knocks the I away from the oxygen, where the I is by itself again. Okay, so let's go ahead and do these one at a time. So A, and it says write the rate law for each elementary step. So for step 1, didn't leave enough room up there, so we'll just do it up here for step 1. Since they're elementary steps, that means the coefficient in front of the reactants is going to be the exponent in the rate law. So for step 1, rate and there it is. The exponents for both are 1 because the coefficients are both 1. Now for step 2. And there are the rate laws for each of the elementary steps. So now B asks to write the overall chemical equation. So this is just employing what we learned how to do in Hess's law. We're going to add these two together to get the overall reaction. Okay, so again, you look for things that only appear once, and the only one I see that only appears once is O2. It doesn't appear anywhere else in either of the reactions, so it's going to show up at the end of the reaction. So I'm going to put it way over here on the right. It's on the right-hand side of the arrow. Now, what else do I see? I appears twice, H2O appears twice, H2O2. Everything else appears more than once. So let's just go one by one. So let's start with H2O. So I have H2O on the right side of this arrow. I'm going to circle my arrows again. And H2O on the right side of this arrow. I don't see H2O anywhere else. So that means they're going to add together on the right side and become 2H2O. Okay, and if you can do things such as check them off that you've used them. Possibly, if you like to do that. Okay, now, what about, let's continue on the right-hand side. We have IO-, and do we see it anywhere else? And yes, here it is on the left-hand side of step 2. So it's on the right side of step 1, on the left side of step 2. Coefficients from both of them are 1. That means they're going to cancel out. Okay. So we've taken care of those. We've basically draw a light line there. We've canceled those two out. Okay, and one more that we have is I-, and that appears on the right side in step 2, and it appears on the left side in step 1. So those two are going to cancel out as well. Okay, and then what else do we have? We have H2O2 on the left side in step 1 and also on the left side in step 2. So we're going to go ahead and go ahead, since we have everything from the right side, we'll put the arrow there, and then we have H2O2, and there's two of them. One there, so we've taken care of those. And that takes care of everything. So that is our overall reaction. Okay, so what was I? I in this one was a catalyst. It appeared at the beginning of step 1, and it appeared again at the end of step 2. So it didn't get consumed during the reaction. That's what a catalyst does. And its purpose is to, in some fashion, there's several ways it can do it. The main one maybe is lowering the activation energy. It provides an alternate reaction mechanism that makes the reaction go faster. And so this is that alternate reaction mechanism, step 1, step 2. Otherwise, all you have is this. And this goes very slowly. This will go very slowly without the catalyst. So how do you indicate the catalyst? You may remember this from some time back, is we put it above the arrow. So it's there, but it doesn't get consumed in the reaction. So you can put it above the arrow, and that will indicate that that is the catalyst. Okay, it says identify the intermediate. So what's the definition of an intermediate? An intermediate I'll write the definition in terms of this reaction, which has just 2 steps. Sometimes you can have a 3-step, even a 4-step reaction. But an intermediate is produced Alright, so an intermediate is produced in step 1 and consumed in step 2, and therefore the intermediate does not appear in the overall reaction. So in this reaction, the intermediate is IO. Alright, so that takes care of C. And D says, assuming that the first step is the rate determining step, write the overall rate law for that. So you remember we did the scenarios with the cups, and what we said was when the situation was that the first step was the slow step, that it produces these things very slowly. The second step is the fast step, so it eats them up right away. It just grabs them and takes them and puts them into a reaction. That's the simplest situation. That's simpler than when the slow step is the second step. And so because this situation, it's simpler because these, as soon as they're produced, immediately go into step 2 and they go through and finish the reaction. So that's the simpler step. So remember, the overall mechanism, the overall rate law for the overall reaction is going to be the same as the rate law for the slow step, as long as it doesn't have intermediates in it, as long as it only has the initial reactant, the actual reactant, which in this case is 2H2O2. So if we look at the rate law for step 1, which is the slow step, it doesn't have the intermediate IO minus in it. It does, however, have the catalyst in it, and we didn't address that. What if the catalyst is there? That's okay. The overall rate law can have the catalyst in it, and of course it can have the initial reactant in it. What it cannot have is the intermediate, which in this case would have been IO minus, and it doesn't. Therefore, that's the answer to the question, that the slow step rate law is the overall rate law. Okay, and there's the overall rate law, which exactly matches the rate law of step 1, the slow step. And that takes care of this problem. Problem 1474, NO catalyzes the decomposition of N2O, possibly by the following mechanism. So the first part, A, what is the chemical equation for the overall reaction? And B, why is NO considered a catalyst and not an intermediate? And then C, if experiments show that during the decomposition of N2O, NO2 does not accumulate in measurable quantities, does this rule out the proposed mechanism? If you think not, suggest what might be going on. All right, so let's go ahead and do that one. So go ahead and write down that reaction on your paper. Is that NO is a catalyst. And so let's go ahead and write that right here. This is a catalyst, and this is a catalyst. That means it's going to appear at the beginning of the reaction, and it's also going to appear at the end of the reaction. It has to appear both places. One thing we see, however, is when you look at it, it's not balanced. You only have one NO there, and you have two NO there. So we're going to have to do something about it. The other thing we see is we have an intermediate. That intermediate is NO2. It appears as a product in step 1 and as a reactant in step 2, but it does not appear at the beginning of step 1. It does not appear at the end of step 2. So that's an intermediate. So I'll just write a little note above that. That means it has to go away. So we see a similar situation that we have two NO2s on the left here and only one on the right here. So we're going to have to get this to be a 2 so that they'll totally cancel out, because we can't have any NO2 left over to appear in our final reaction. So the way we can take care of both of those issues is by multiplying all of step 1. And remember, this is just one of the rules of chemical reactions that we learned in Hess's law. You can multiply that through by a factor. So we're going to multiply that by 2. So I'm going to come down here and rewrite step 1. Okay, you don't have to do all the writing I'm doing. I just want to be sure it's very clear what it's going to look like. You can shorthand it a little bit if you'd like. So what I end up here is 2NO. I'm back in step 1. I end up with 2N2O. And I'm going to go ahead and rewrite step 2. I'm not going to change it at all. I just want to put the two back together again. Now we can go ahead and add those two to give the overall reaction. Alright, so the 2NO2 cancels. Those are intermediates, and we needed that to go away because they don't appear at the beginning here or at the end here. The 2NO also disappears because it's a catalyst. So let me write what these were. This is an intermediate. It's not at the beginning of the reaction. It's not at the end of the reaction. This is also the intermediate. So it ends up disappearing, being made and then disappearing in the middle of the reaction. That's the definition of an intermediate. The definition of a catalyst is just the opposite. It appears at the beginning of the reaction, and it appears also at the end of the reaction. And we see that happening here. But we don't write it as part of the chemical equation. You remember what we do. We put it above the arrow if we're going to show it at all. Okay, so the catalyst is going to cancel out. So we're left with this, this, and this for our final reaction overall. So we're going to write that. And that is the overall reaction. You can see it is balanced. And if we want to write the catalyst up top, we can just write NO. You don't have to write any coefficients on it. You're just showing that it's a catalyst. Okay, that takes care of step A. We'll label that. Down to B. Okay, why is NO considered a catalyst and not an intermediate? So let's go ahead and just write out the entire explanation of that and be sure we're clear on that. I'd like you to write the whole explanation. A catalyst increases the rate of a reaction. Okay, so a catalyst increases the rate of a reaction. It appears in the reactants of step 1 at the beginning of the reaction and in the products of step 2 at the very end of the reaction. It appears in both places. So a catalyst is not consumed by the reaction. And intermediate is produced in step 1 and consumed in step 2. So it's produced in the middle of the reaction and consumed in the middle of the reaction. So it does not appear anywhere in the overall reaction. Okay, and finally, I'm going to reread C. It says, if the experiments show that during the decomposition of N2O, NO2 does not accumulate in measurable quantities, does this rule out the proposed mechanism? If you think not, suggest what might be going on. Well, no, it definitely doesn't rule out the proposed mechanism, because what it means is, similar to the previous problem, that we're producing the NO2 here, it's being consumed in step 2. It's the intermediate. So if this is the slow step, the first step is the slow step, just like the last problem we did, and the second step is the fast step, then that's exactly what you would expect. You would expect no NO2 to be building up inside of your vessel where the reaction is taking place. As soon as NO2 is made, it's immediately consumed by step 2 because that's the fast step. So this produces slowly. As soon as something is produced here, though, it's gobbled up by step 2, and so you don't have any buildup of NO2. If the first step were the fast step, you might have a buildup of NO2 because the slow step, being the second step, would not gobble it up quite as quickly. And so some of it would actually go back to reactants there. Some of it would just kind of sit there as NO2 for a while, waiting for step 2 to pick it up. That's if the second step was the slow step. But no, if the first step is the slow step, you produce a little bit very slowly, and then as soon as you produce it, this fast step, the next step will eat it up and go ahead and complete the reaction. So no, it doesn't, in no way does that mean that the proposed mechanism is not correct. So let's go ahead and write that out. I won't do the explanation about the second step being the slow step. That's not part of the explanation here. I'll just write out the first part. So Okay, so as long as step 1 is the slow step, the NO2 will be produced slowly. Step 2 will consume the NO2 as quickly as it is produced, step 2 being the fast step. As a result, we would not expect to see any buildup of NO2. Therefore, the absence of any buildup of NO2 does not rule out this rate mechanism. All right, so that takes care of this. It's a fairly long assignment, but it covers everything you really need to know in kinetics. Save this assignment, in the spring. This is something you can go back and work these problems again. And if you can do these problems, you can do pretty much anything they would ask you to do on the AP in kinetics. All right, so I'll see you in class on Monday. Have a good weekend.